Hello everyone. Good morning, Suprabhat and Namaskar. I am Alok Chandra Mohanty and I have the pleasure and privilege to welcome you all to the 2 days international seminar organized by the Department of Mathematics on the topic Application of Mathematics in Science and Technology under the aegis of DBT Star College Scheme. Thank you for joining us for today's seminar. Now I request our Honorable Principal, Dr. Umesh Chandra Pati, to deliver the welcome speech. Please, sir.
Good morning. Thank you, Alak Babu. Good morning to you all. Namaste. Hope all to stay well. At the outset, I extend a very warm welcome to all the participants and my deep sense of gratitude to two experts, research persons of the international webinar being organized by Department of Mathematics in 2 sessions today. And the research persons are Dr. Tarakant Nayak in the first session, Associate Professor, School of Basic Science, IIT Bhubaneswar. He is our alumni. We have regular academic exchange and regular interaction with him. As the prominent alumni of our college, he has his academic contribution in addition to the monetary contribution, and he is our Board of Studies member for a long period of time. Our second guest, our second speaker, second expert research person in the next session is Dr. Rabindra Kumar Jana. He is the professor and area chair on Information Technology and Business Analytics, Institute of Management Technology, Nagpur. So I extend a very deep sense of gratitude and my welcome to these two research persons who have accepted our request to share their views with regard to two mathematical topics. One is where do fractals live, to be delivered by Dr. Tarakant Nayak, and next one, explainable artificial intelligence, to be delivered by Dr. Rabindra Kumar Jana. And I hope that the participants, they will gain a lot through interactions among these participants and also with the research persons. And as it has been highlighted by our Professor Alok Chandra Mohanty, that this international webinar is organized under the aegis of the DBT Star College Scheme. So I should emphasize here that Salehpur Autonomous College Salehpur is the only college being selected for 3 years from the current session 2020-21 under Star College Scheme. Department of Physics, Chemistry, Mathematics, Botany and Zoology, they have been provided with funds to develop the academics, teaching, learning and research, exchange of ideas, all these activities to develop academics in Salehpur Autonomous College in particular and in the academic society in general. And we all know that research doesn't involve any type of big equipment, big computer facility or technology. It is application of mind, and that will be vibrated by the research persons, by the senior mathematicians, by the senior experts. Our college is 56 years old, so also the Department of Mathematics with conferment of autonomous status and the assistance being provided by the government of Odisha under IDP assistance, World Bank assistance. We are working ahead to develop the tempo of academics in our college, and I hope that all these two experts who are here today, they will have their good touch with us. And also I hope that all these research persons and the experts who are there involved in the process from time to time, they will extend their helping hand to the institution to develop academically, to develop students' research facilities, exchange of teachers and students among different institutions and so on. Thank you all. I again welcome to all the participants and my gratitude to the research persons. Thank you all. Now over to our Alok Babu to continue this process. Thank you.
Thank you, sir, for your very interesting and thought-provoking welcome address to our participant on this webinar. And I, on behalf of the Mathematics Department, must mention our deep sense of appreciation and would like to express our profound gratitude to you, sir, for your presence in this e-meeting in spite of your busy scheduled office work and radiate a source of energy with us again. Thank you, sir. Now I request our beloved head of the department, Dr. Sangeeta Mishra, to introduce the eminent and ardent resource person of this session, Dr. Tarakanta Naik. Over to Madam. Please, Madam.
Hello. Good morning, everyone. Esteemed patron of this webinar, Dr. Umesh Chandrapati, Principal, Salepur Autonomous College, respected resource persons of this webinar, and respected members of organizing committee, web designer, and all the participants. First of all, I welcome everyone to this international webinar on the topic Application of Mathematics in Science and Technology, organized by Department of Mathematics under the aegis of DBT Star College scheme on 15th and 16th December 2020. Our esteemed resource persons are Dr. Tarakanta Naik, Associate Professor, School of Basic Science, IIT Bhubaneswar, Dr. Rabindra Kumar Jena, Professor and Area Chair, Information Technology and Business Analytics, Institute of Management Technology, Nagpur. Dr. Siddhar Naik, Associate Professor, Disaster Prevention Research Institute, Kyoto University, Japan. Dr. Debashish Pradhan, Assistant Professor, Defense Institute of Applied Mathematics, Girinagar, Pune. It is a great pleasure and honor on my part to introduce the resource person of this session, Dr. Tarakanta Naik, will deliver on the topic, where do fractals live? Dr. Tarakanta Naik is presently working as Associate Professor in Mathematics in School of Basic Science, IIT Bhubaneswar. He had joined the IIT Bhubaneswar as Assistant Professor in Mathematics in 2010. His academic experience spans over a period of 13 years in top institute. He started his academic career in National Institute of Technology, Rourkela, as Assistant Professor in 2007. He has completed postdoctorate at Tsinghua University, China from 2008 to 2010 and was a postdoctorate fellow in Harishchandra Research Institute, Allahabad from February 2007 to December 2007. Dr. Naik completed MSc from Utkal University in 2001 and did his PhD in mathematics from Indian Institute of Technology, Guwahati in 2007, with the thesis title as Dynamics of Certain Transcendental and Meromorphic Functions, under the supervision of Professor M. Guru Prem Prasad. His area of research interest are complex dynamics, independence polynomials, and fractals. He guided many research scholars, and 2 of them got PhD awards, and 1 got postdoctorate award under his guidance. He also guided more than 50 MSc scholars inside and outside IIT Bhubaneswar. During his illustrious career, he has completed interesting sponsored projects from Government of India and Government of China. Some of these projects are titled as Topological Aspects of Transcendental Dynamics, Julia sets of transcendental meromorphic functions, omitted values in complex dynamics, and independence polynomials of graphs and associate fractals. He has received many honors and awards for his excellence in field of mathematics, prominent among which are the Ramanujan Prize in 2018, awarded by Ramanujan Institute for Advanced Studies in Mathematics, University of Madras. He is also selected as a member Indian National Young Academy of Science from 2018 to 2022, and also awarded the postdoctoral fellowship by National Board of Higher Mathematics in 2007. He has presented and published several research papers in national and international journals, conferences, and workshops. Some of his notable publications are Graphs whose independent fractals are line segments, Bulletin of Malaysian Mathematical Science Society in 2020, Iteration of the Translated Tangent, Bulletin of Malaysian Mathematical Sciences Society, Harman rings with small periods and omitted values, Acta Mathematical Scientia series, and iteration of certain exponential like meromorphic functions, Proceedings of Indian Academy of Science, Mathematical Science, and many more papers. He acts as a reviewer for the mathematical reviewers in American Mathematical Society and has visited many countries. Prominent among them are Italy, Malaysia, and China. I am very glad to inform you that Dr. Naik did his BSc course in Maths Honours from this college in 1996 to 99. I sincerely hope that his vast experience in the field of mathematics will enlighten you today's webinar. Thank you.
Thank you, madam, for your introducing speech. Now I am extremely honored and privileged for getting an opportunity to focus on the theme of the topic, where the fractal lives. So now I read out the theme of the present topic. So here we have the interesting topic named Where Do the Fractal Live? For the first session today will be presented by Dr. Tarakanta Naik, who is an alumnus of this college. In this present context, this emerging topic is very much beneficial for the participant, including students, researchers, and academicians. In mathematics, fractals are the class of complex geometric shapes that commonly have fractional dimension, introduced by the mathematician Felix Hausdorff in 1918. This word fractal derived from the Latin word fractus, that is fragmented or broken, was turned by the Polish-born mathematician Bernard B. Mandelbrot. Many fractals possess the property of self-similarity, at least approximately, if not exact. Fractal dimension is a key property and an indicator of the complexity. It is a new branch of mathematics and field of art. This is the reason for most people are fascinated by the beautiful images termed as fractals. Extending beyond the typical perception of mathematics, As a body of complicated and boring formulas, fractal geometry mixes art with mathematics to demonstrate the equations that are more than just a collection of numbers. The most interesting part of fractals is that the existing mathematical description of many natural forms like coastline, mountains, or parts of living organisms, the history of fractals traces a path from chiefly theoretical studies to modern applications in computer graphics, with several notable scientists contributing their canonical fractal forms along the way. The features of fractals is a geometric object generally has of fine structure at arbitrary small scales. Second one of irregular and rigid described in Euclidean geometric language. Third one of self-similar. Fourth one of Hausdorff dimension. Fifth one of simple and recursive definition. The common techniques used for generating fractals are fractal generating programs. Second one is iterated function system. Third one is strange attractors. Fourth one is L system techniques. Fifth one is finite subdivision rule. Sixth one is stochastic rules for generating random fractals. Seventh one is recursion relation, generating escape time fractals. Actually, fractals are classified into 4 types of self-similarity. There are exact, quasi-statistical, and qualitative. Fractals permeate our lives, appearing in places as thin as the membrane of a cell and as majestic as the solar system. These are unique, irregular patterns left behind by the unpredictable movement of the chaotic world at work. So fractals live everywhere on this world. For example, the branching of tracheal tubes, leaves in trees, vents in hand, water swirling and twisting out of a tap, a puffy cumulus cloud, tiny oxygen molecule, the DNA molecule, the stock market, astronomy, and also snowflakes, broccoli, cauliflowers, airways in lungs. The application areas of fractals are in medical science, in arts and music, architecture, geology, geography, archaeology, seismology, fracture mechanics, electrical engineering, signal and image compression, cryptography, astronomy, computer science, fluid dynamics, telecommunication, and everywhere it was seen. Many scientists have found that fractal geometry is a powerful tool for uncovering secrets from a wide variety of systems and solving important problems in applied science. But for general people, fractals will never represent anything more than beautiful pictures. Lastly, in this theme presentation, I only describe about fractals, but the topic is on where do the fractals live. So I request all my learned participants to listen patiently and grasp the concept of fractals from the talk of our eminent resource person, Dr. Tarakanta Naik sir. I request Tarakanta sir to deliver your talk. Over to Tarakanta sir. Thank you. A second.
Am I audible, sir?
Yes, yes, sir.
Okay, thank you. Should I start? Hello, sir. Should I start?
Yes, sir, start.
Okay. Thank you, Alok sir, for touching almost every idea that I am going to speak today in these few minutes. And also thank you, Madam, who taught us mathematics when we were almost nowhere in the world of mathematics. And yes, this webinar reminds me our college days in the river bank and in the college campus on Sundays. मोटामोटी से सब कथा मन पड़ुची खुशी लगुची ओके धन्यवाद समस्त को सर मान को okay let me start so I think Alok sir I have around 40 minutes right sir
Okay. You carry on.
okay
You take 45 minutes.
okay
Hello. Tarakan sir, carry on.
okay I just want to find how to move the slide in this case. Slide ta move केमती हबो no.
Sir, okay, it is visible, sir.
It is visible, but I am trying to find out how I can move the slides.
Sir, up arrow, down arrow. From the keyboard, there are 4 arrows. Left arrow, right arrow, up arrow, down arrow. Then if you want to go to top, then press up arrow, sir. Or by using the scroll bar, you can move the... yes, sir. In that way, you can move it. Okay.
Okay, so
Yes,
the
sir.
topic is where do the fractals live? So Alok sir has already introduced what a fractal is or what a fractal can be. So let me continue. Okay, so I will be basically dealing with the mathematics behind fractals and the space of fractals, where they are and where we can talk of convergence and thereby approximating the natural objects like the mountains, coastlines, cells, and so on. So let me first start with some basic ideas which is required for talking fractals. So first thing, we know what a metric space is. So what is nothing but a non-empty set X, any set, and a notion of distance that we call D. Mathematically, we all know that this D, the notion of distance, is nothing but it is a function from the Cartesian product of X to the set of positive numbers including 0. This is how we give a notion of distance to a non-empty set. So by that I mean, if I take 2 points from X, XY, I should be able to associate a non-negative real number to those 2 points. And that is what we understand as the distance. But yes, there are some requirements from this function In other words, it is not that you just take any function like this and that will give you a distance. No. What are the requirements? Requirements are that the distance between x and y should be equal to the distance between y and x, which is usually required. And of course, the distance of any point from itself should be 0. And lastly, the triangle inequality, distance between any 2 points in the set is less than equal to the distance between x and some other point of the space plus distance between that other space and z. So this definition, yes, this is motivated by our usual distance in R2 in the plane, which is given by this formula, the Euclidean metric. The distance between 2 points x1, x2 and y1, y2 in the plane, we know this is x1 minus y1 square plus x2 minus y2 square root over the Euclidean metric. And our general notion of a distance in any space, not necessarily R2, is this. This is nothing but the generalization of our Euclidean notion of distance. So yes, in mathematics, we don't like to be restricted to restrict ourselves. So here, our space, this X is not necessarily R2, it can be R3, R4, and it can be a space of functions, it can be a space of matrices, it can be just anything, as long as it is a non-empty set and as long as you are able to define a function from the Cartesian product of X to itself to non-negative real numbers satisfying these three things. So this is our metric space. And yes, this is the natural example of a metric space, Rn and this Euclidean distance. What is important for us in this talk is the so-called complete metric space. Those are nothing but the metric spaces where every Cauchy sequence converges. So what is a Cauchy sequence? A sequence Xn, this is just to remind you, a sequence in the metric space X is Cauchy, or we call it Cauchy, if for every epsilon bigger than 0, if it is possible to find a natural number n such that for all n m bigger than capital N, the distance of the terms of the sequence xn, okay, let me call it xk then. Then the term of the sequence after this capital Nth term, the distance is less than epsilon. This is the definition of Cauchy sequence. That means the tail of the sequence are such that the terms not necessarily conjugative. I mean, this n and m, they are not necessarily differing by 1. They can be far apart. Say n can be 100, m can be 1000. But irrespective of that, if it is possible to find some stage in the sequence so that after that all the terms are sufficiently close to each other, we call that Cauchy. Note that Cauchy is not obviously giving you convergence, but yes, it gives in metric spaces. And those metric spaces where any such sequence is convergent, we call it a complete metric space. So the space, the world where fractals live, which we are going to discuss today, we require it to be a complete metric space. We give a suitable metric to it, and it's a complete metric space, and we'll see how what kind of sequence can converge to a so-called fractal. Okay, let us proceed. Before we proceed, and before we actually catch hold of the space of a fractal, let us slightly generalize our idea of Euclidean distance. And as Alok sir has already mentioned, it is named after that famous and extraordinary mathematician Hausdorff. Okay, what is the generalized notion of distance? Okay, you take a any metric space X, and you just take two compact subsets of it. So by compact here, actually my X throughout this talk is going to be R2. So any compact subset of R2 are nothing but closed and bounded subsets. That's all. In more abstract notion of topology, they are such subsets of X such that every open cover has a finite subcover, but anyway, that is equivalent and simplified to closed and bounded subsets of X. So if I take two compact subsets of R2, then what I'll do, I fix B and I take one element in X, so in A. So I have X, and say B is something like this, B my compact set. Okay. Now, what can be the distance between a point and a set? Yeah. So I define that to be the infimum of all the distances from X to any point of B. So if I take a point small b here, the distance is this. If I take small b here, distance from X is this. But then I will take the infimum of all these distances which seems to be achieved at this point. So this length is dxb, at least in this picture. Okay. So this is how I define distance between a point and a set, compact set B. Now, what is the distance between two compact sets? I will take, okay, now let me take a set, something like this, everything inside. So let this is A, this is B. Okay, let me take B to be good looking. Yeah. So now what we'll do, I will fix a point small a here, and I will find all DAB, DA capital B. So as it seems, the DA capital B will be this distance, right? The minimum, the infimum of all the distances from A to any point of capital B. So for this A, I get a distance, this is like D, A, small a, capital B. Then if I change this A, say I take it here, then for that, this DAB is going to be different. Maybe this looks like this distance is this. Then what I will do, I will take soup of this, soup over what? Soup over small a. So I collect all those distances and I take the, in a sense, the largest. That is my distance between two compact sets. So, okay, let me look at this example to give you a better idea of what exactly this new notion, this is not new, this is a different generalized notion of distance. Okay, let me take this is 0, this is 1. So this point is 0.5, set A. So set A is the singleton point consisting of 0.5. And let me take B. So this is 2, this is 3. B to be consisting of the sequence Bn union 3, because B need to be compact. So what are the points of capital B? When n is equal to 1, what is this? This is, okay, let me write it x1. What is x1? x1 is 3 plus minus 1, 1 by 2. So 3 minus 1 by 2, that is 2.5, right? Yes, that is 2.5. So if this is 2, this is your x1. What is x2? X2 will be 3 plus minus 1 to the power 2, that is 1. So 2 by 5. 3 plus 2 by 5. So 3.4, right? So if this is 4, 3.4 is something here, x2. Then x3 will be 3 minus 3 by 10, right? So that is 3 minus 0.3, that is 2.7. Something here is x3. Okay. So then x4 will be in the right hand side of 3, x5 will be in the left hand side of 3, and so on. Finally, the sequence small bn converts to 3, and 3 is there in the set. Okay. Now, what is this D? So capital A consists of the single point 0.5. So what is this D small a b? This is the minimum distance from 0.5 to this set capital B. And in capital B, the point x1 is nearest to this point. So DAB, just a minute, excuse me. So ମୁଁ ଟିକେ ମୁଁ ତତେ ଅଧ ଘଣ୍ଟା ପରେ କରୁଛି। हाँ हाँ ओके 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 हाँ ओके ओके okay okay. So this DAB is this distance, right? Distance between 0.5 to x1, that is 2, right? And if I take supremum of this over, I am taking AB, capital A is my singleton. So if I take a supremum over capital A, I will get this 2 only. And this is nothing but the distance between A, B, right? So if my A is singleton 0.5, capital B is this set, I see that DAB is 2. But what is DBA? If I take any point in capital B and look at its distance, then say I take x1 in capital B. So this distance is, yes, this is 2. But if I take x2, this distance is, what was x2? X2 was 3.4, I guess, yes. X2 is 3 plus 2 by 5, yeah, 3.4. So if I look at supremum of this, I will see that supremum is attained for 2 points, 0.5 here and 3.4 here, and this is actually 2.9, and that is by definition distance between BA. Hello? Tikke adha ghanta pare kochi talk range. Okay, so as it is remarked here, this DAB is not equal to DBA, at least for this example. Yeah. So how can we define the idea of distance on the space of compact subsets of a complete space? That is where the Hausdorff distance come in, and we define the distance between two compact sets to be the max of DAB and DBA. So in our previous example, the distance between singleton 0.5 as A and B to be that sequence of numbers, it is 2.9. And one can see that this satisfies the three properties of metric, and hence it is a metric space. But what does this mean by saying that the distance between the two compact set is maximum of DAB, DBA? What does this mean? This means the following. Note that here, okay, let me take this same example again, and let us try to make sense what this distance actually tells us about the nearness of these two sets. This tells us that what you do, you look at a delta neighborhood of A. What is a delta neighborhood of A? You take all the points of small a and take balls of radius delta and take their union. For example, here in this picture, a delta neighborhood of A will be an interval like this, whose center is 0.5. This point is 0.5 plus delta. This will be 0.5 minus delta. Okay. And a delta neighborhood of B will be what? Will be an union of intervals about this BNs. BN minus delta, BN plus delta, interval, union over N. And of course, 3 we should take, 3 minus delta, 3 plus delta. So this set for us is B delta. Actually, this number dxb, what it is? It is that number delta such that A is a subset of B delta. Because here, if you take all the small b's in capital B, take intervals around those points, and take the union of the intervals, that union will contain this X. Yeah. So, in other words, this number is nothing but the smallest delta such that A is in B, A is in delta neighborhood of B, and B is in delta neighborhood of A. That means in another picture, if you take this as A, then your delta A will be union of all these delta balls centered at all possible points of A. So it is a kind of patterning of A. And similarly B, if it is a set like this, its patterning will be something like this. It's patterning. So when we say that Hausdorff distance between these two compact sets is something, we mean that something is such a number, which is the smallest number, so that when you pattern A by that number, that will contain B, and when you pattern B by that number, that will contain A. So in this case, if you take your A to be something like this, then a patterning or a delta neighborhood of A which will contain B will be like what? Will be like something like this. But if one delta patterning of A contains B, then bigger patternings of A will also contain B. That is why smallest is important. Okay. Similarly, if you pattern B by that number HAB, then B's patterning will be looking like something like this, right? and that should contain A. And we collect all those deltas for which A is subset of a B delta and B is a subset of A delta, and we take their minimum or smallest value, that is this Hausdorff distance. And this is the distance used by people to discuss nearness of two fractals, or to say when two fractals are close to each other and so on. So here is the world of a fractal. For our purpose, X is R2, but you can take it as Rn without loss of generality, without any new idea. So for us, it is R2, and we look at all non-empty closed bounded sets. So we are talking about fractals living in the plane. That is why this is our world of planar fractals. I mean, which can be viewed as a picture in a piece of paper or on the computer screen. But yes, no one wants to be restricted. You can look in the same way as three-dimensional fractals, which are actually the boundary of a hill or the coastal line. Coastal line can be thought of as planar fractal, but the boundary of a cauliflower, the boundary of the distance hill, they are three-dimensional things. So they live in HR3. Okay. Now, this Hx, the set of all compact subsets with this new notion of a distance, Hausdorff distance, is complete whenever xd is complete. Yeah, whenever xd is complete. Oh, I cannot write anymore. Okay, so if we start with xd, a complete metric space, then this space is also complete, and we can talk about the convergence and nearness of fractals. So I am not proving this. This can be found in the famous book. Alok sir has already mentioned that there is a book by M.F. Barnsley called Fractals Everywhere. So all this material are taken from that book. It's a very nicely written book, and you can read that. Okay, now let us look at a particular type of nice map. Those are called contractions. Contraction, you know, I mean, this map, if you give it a set, then its image set, if this is a set, then the contractions are such that its image will be something smaller than this, something smaller than, and so on. They are called contractions. So metric space xd is there. A function is called a contraction if the distance between the image of any 2 points is less than equal to s into distance between the points. S is, this should be 1. S is a number between 0 and 1. So that the distance between the image points is strictly less than, this is strictly less than distance between the points. So this is called a contraction. For example, yeah, here is the example. If you take x to be c, and fz is given by iz by 2, and if you take 2 points z1, z2, look at the distance between them, then that is I by 2 modulus into z1 minus z2 modulus. And clearly I by 2 mod is less than 1. So S can be taken as half in the definition, and this is less than z1 minus z2. This is an example of a contraction in C. And in R3, R4, you can get maps defined in terms of matrices. We'll see them. They are contractions. So my point is that contractions are there. This S, which is not uniquely defined here, because for example, here when S is half, you can also say, okay, I can take S to be 1 by 3. That will also work. So any such X, we call it a contractivity factor of F. It contracts a set by this factor. And by epsilon delta definition, it is not difficult to see that any contraction is a continuous map in fact, not only continuous, it is a ellipsis map. It is uniformly continuous on compact sets. So my point is that contractions are easy and nice maps. Not only that, they are useful maps for us. Now, this is contraction mapping principle, which says that, okay, you take any complete metric space, you take any contraction, always there is a point in the space which is fixed, meaning x0 equal to 0. It is its own image. So it is there. So every contraction map in a complete metric space has a fixed point. This is the famous contraction mapping theorem, and the proof is not at all difficult, because we can show that by showing it is any Cauchy sequence. Okay, any Cauchy sequence converse that is given to us, existence of fixed point can be proved this way. You just take any m bigger than n, the distance between xm, xn by contraction map. So what is xm? Xm is the mth iteration of a point x. So we start with a point x. X1 is its image, x2 is its image of the image, and so on. This is called the forward orbit. So we can see that the distance between xm and xn is less than equal to s into xm is the image of xm minus 1, xn is the image of xn minus 1. So this we get because f is a contraction with contractive factor s. Similarly, we can apply the same argument here, because f m minus 1 is the image under f of xm minus 2. Similarly, another s will come. So s square into d xm minus 2 xn minus 2. Similarly, we can finally arrive at a stage where s to the power n is there, and here, since I have taken m is bigger than n, so this is n, this is n plus 1, somewhere this is m, and it will stop here, x m minus 1 x. And then this x m minus 1 n x, I can apply triangle inequality, x x1, x1 x2, and so on, so that x m minus n minus 1, x m minus n, that distance. And after that, taking x, applying contraction definition here, this is less than s into distance of x and x1. This is less than s square into distance of x1 and x, and so on. So taking this common, I will get this so-called part of the geometric series. And since this is a finite number and s is positive, so this series is less than equal to this infinite series. This term remains same, and this series is nothing but this, right? Because s is a number between 0 and 1. So geometric series converge and converge to this number. So what we get, that for m bigger than n, distance between xm and xn is less than equal to Sn, n is the smaller number than m, into dxx1 1 minus s to the power minus 1. So this proves that the forward orbit of x, namely this sequence, is a Cauchy sequence. And since x is complete, this converges and converges to a point, and this forward orbit of any point, this is important. You take any point, its forward orbit tends to this unique fixed point. This is unique because if you take two fixed points, then their distance between their images, which is distance between themselves, cannot be less than equal to s into this, because this quantity is equal to this, and s is something smaller than 1, so this cannot be true. So for contraction mapping principle tells us that in a complete metric space, if you have a contraction mapping, there is a unique point somewhere here, so that you start from any point, look at its forward orbit, repeated application of the function on that point, then you will get a sequence converging to this. You start from here, it will also converge converge to that unique fixed point. So this is contraction mapping principle or theorem. You can get it in Walter Rudin book of mathematical analysis. Proof is the same. So how these contractions work? Okay, note that this first black part under a contraction becomes the second black part, and then third, and so on, and finally it converts to a point. This is a schematic pictorial description of how a contraction in a metric space work. Okay. Now in the space of fractals Hx, we have a nice contraction. How is that? Okay, you first start with a contraction in X. X is any metric space, W is a contraction with contractive factor S. Then from this contraction, we can get a contraction of Hx. Hx is the set of all compact subsets of X. If it is difficult to visualize the abstract thing, you can just take X to be R2, that's enough. How W is defined? W is defined by this. W of a compact set is the set of all images of that compact set under W, that's it. And it can be seen that W is a now function from Hx to Hx, and this is a contraction on Hx. I am skipping the proof just to spend some more time on some more important thing. So the whole point is that if W was a contraction on X, then this W is also a contraction on the Hx with the same contractive factor. These are just elementary argument using the definition of Hausdorff metric. So the point again, I repeat, if I have a contraction on a metric space, by that contraction I can get a contraction on the space of all compact subsets of that metric space. That's it. Now, again, this iterated function system has also found a mention in Alok sir's introduction. What is an iterated function system? It is nothing but a complete metric space and finitely many contractions. That's all. So simple a definition. So you have a complete metric space and W1, W2, W capital N, finitely many contractions. And let me assume that Wi has contractive factor Si. Then we can define a map from Hx to Hx by this. What is this? So suppose I have a B, capital B. I have an iterated function system. So suppose W1 takes capital B to something. W1B. W2 takes it to something, it may intersect. Okay, so this is W2B. Then W3 and so on. So you take the union of all the images of small wi's, and this union is the image of this new map capital W of B. To define this way. Then this capital W can also be shown to be a contraction with the contractive factor maximum of Si. And now by contraction mapping principle defined to this W on the space of fractals says that in this space of fractals Hx, where X is given by this, has a unique fixed point. That means if you take X, you take all compact subsets of X, then you start with any compact subset of X, say B, and apply W on that. So the capital WB, capital W square B, and so on. This sequence of compact sets will converge to something. And that something is famously known as the attractor of the iterated function system. And this attractor is actually and usually a fractal. And the nature of this fractal, its dimension, its shape, is determined by this Wi's. Okay, let me go to that. So here the main question that I want to address here, okay, a natural picture is suppose given to you. Suppose I give you picture of a coastline. Then I ask you, can you give me a mathematical description of this? It's not possible because coastline is highly irregular. And taking a picture of the coastline and sending it, sometimes it is costly. It requires lots of space in memory. So there is a way out. Namely, this is also called the image compression. That means in essence, describing an image by some numbers and maps, so that if you want to transfer the image, you can just transfer the maps and the set to your friend, and he can just recover the image. This is image compression, right? Transmitting images, actually not sending the image themselves, but coding them in essence. So that is possible by this Collag theorem, that is again by Barnsley, and I think this is proved in 1985 by M.F. Barnsley, who also set up a company called Iterated Function Inc. Anyway, that's a different story. So what is this? You take a complete metric space X, then you take any subset of Hx, any compact set. Then for that compact set, if you can choose an IFS, X is already there. If you can choose some finitely many Wi's, so that the distance, Hausdorff distance between L and WL is less than epsilon. Epsilon is given. So let me repeat. L is given and epsilon is given. So say my L is something like this. My L is like this. It is given to me. For an epsilon, if I can find a set of finite Wi's, which are contractions, so that the distance, Hausdorff distance between L and its image, something like this. If the Hausdorff distance is less than epsilon, then this L is at most epsilon by 1 minus s apart from the attractor of IFS. What does that mean? That means given any set in Hx, in other words, given any compact non-empty subset of X, it is always possible, or if it is possible, to find an iterated function system which does not take L far apart from itself. I mean, image of L and L, they are not more than epsilon apart with respect to Hausdorff distance. Then that iterated function system, if you look at its attractor, that attractor is also close to L. In other words, you can approximate any given compact subset of X by what? By the attractor. So by the attractor of an iterated function system. So if it is so, by taking the iterated function system, you can say, okay, this iterated function system has this attractor, and by this I can approximate this given L. So what you did basically for a given L, you found an iterated function system that contains all the required informations to generate L at least approximately. And larger iterations of capital W you take, closer you will become to your predetermined L. So this is how you can approximate any fractal, because this L can be a fractal. Any shape, just it need to be compact, that's it. This can be approximated by an attractor on of an iterated function system. That way, changing a fractal to an iterated function system. What is an iterated function system? Just a set and finitely many maps. That's it. So I will, before I stop, I will look at a very, very trivial example, namely the Cantor set. You take X to be R. You take these as 2. Oh, this is 3. This is 3. If you take this as the iterated function system, then what will be W of 0, 1 closed interval? The 0, 1 closed interval by W1 will become 0, 1 by 3. By W2, it will become 1 by 3. No, this is 2 by 3, sorry. So this will be W1, this capital I, this is capital I, and this is 2 by 3 to 1, this is W2 capital I. So their union is this. Then again, when you apply W2, what you get? You will get this thing, and this thing, and this thing, and this thing. And when you go on, what you get is nothing but classical Cantor ternary set. And that is the attractor of this iterated function system. Okay. But yes, when S is 3, this is Cantor ternary, but by taking S equal to 4 or S equal to 2, one can play to get the sets like Cantor set, but which are not Cantor ternary. Okay, and if you take R2 and these 4 maps defined this way and iterate, your attractor is going to be a picture like this. This is Barnsley. This is famously known as Barnsley's thorn. So such a leaf or part of a tree can be expressed as R2 and 4 maps, W1, W2, W4. And there are many more. I'll just stop this. This is not stopping. Okay, so I'll stop. I will show this at the end. So these are the 2 books. Actually, this is the book from where all the contents are taken. This is also a nice mathematically written book, not very difficult, by Falconer. And let me show you a minute. First, I will stop by showing you one link where you can see many other pictures. Okay. This is the website where you can find many, and these are the approximations of the attractor of an IFS, and finally it takes so one can play with different parameters of the IFS and find fractals of this set. This is called tweak, and a branch of the tree can also be generated by modeling it as an attractor of an IFS like this. This is known as crystal, and there are many more. Okay. So with this, I thank you for a patience full hearing. And if there are any question, I will like to try to answer them.
Thank you, Tarakanta sir, for your enlightening and stimulating speech. It was the best, witty, excellent, elaborative and informative presentation about the metric space to define a fractal. Sir, you have already discussed about the College theorem, Cantor set, and metric space. Again, define the originate the fractals. So, thank you, sir, for your kind presentation. And those who are interested on fractals, they can follow the email of Tarakanta sir. Thank you, sir. We have a questionnaire session at the end of the 2 sessions.
Okay, fine.
Now, this is the time for introducing our next erudite, savant and eminent resource person, Dr. Ravindra Kumar Jena from IMT Nagpur. Sir, Dr. Ravindra Kumar Jena, born in 1970, is presently working as professor and area chair, Information Technology and Business Analytics, Institute of Management Technology, Nagpur. He is also a visiting professor to Telecom Business School, Evry-Essonne, France, and Institute of Management Technology, Dubai. He has received his PhD in Information Technology from Indian Institute of Information Technology and Management, Gwalior, India. His areas of interest entail soft computing techniques, data mining, business intelligence and analytics, big data analytics, blockchain technology. He has published more than 60 research papers in national and international journals of repute. The quality of his papers can be measured by the fact that many of his publications were given an impact factor of more than 3 by the Thomson Reuters Journal citation reports, and on an A or A star category in the Australian Business Deans Council list. His academic experience spans over a period of more than 20 years in top institutes of country and abroad. He has been the editor of International Journal of Innovative Research in Science and Technology, IMT Nagpur, India. He is also guest editor of many international journals, including International Journal of Information System and Social Chain, International Journal of Asian Business and Information Management, and International Journal of Knowledge-Based Organizations. He has been the editorial board of prestigious journals like Interdisciplinary Journal of Information, Knowledge and Management, Information Science Institute, California, USA, and International Journal of Asian Business and Information Management, IGI publication, USA. He has presented and published several research papers in national and international conference and workshop. Some of his notable publications are an empirical case study on Indian consumers' sentiment towards electric vehicles, a big data analytics approach, industrial marketing management, and measuring the impact of business management students' attitude towards entrepreneurship education and entrepreneurial intention, a case study, computers in human behavior. In addition to participating, he has chaired and organized many international and national conferences. He is pertinent to mention that he chaired a session in Reconfigurable Architecture 1, 4th International Conference on IT, New Generation, Las Vegas, USA, in the month of April 2nd to 4th, 2007. He has authored a book titled Design Space Exploration of Network on Chip at System Level, Academic Publishing, German, 2012, and has also edited many books on information technology. He has visited more than 20 countries, prominent among which are France, USA, Germany, and Switzerland. I am sure Dr. Jenna's vast experience in the field of information technology will enrich the participants in today's webinar with knowledge and perspectives. Thank you, sir. May I request Professor Prashant Kumar Jenna to focus on the theme of the topic that will be ventilated by our resource person, Explainable Artificial Intelligence in nutshell. Relay microphone to Prashant sir. Sir, please.
Welcome to all participants, and also to resource persons, Professor Dr. Tarakanta Nayak sir and Professor Dr. Rabindra Kumar Jena sir. Now we have another interesting topic named Explainable Artificial Intelligence, shortly known as XAI, for the second session today, that will be presented by the notable Professor Dr. Rabindra Kumar Jena from IMT Nagpur. Recent times in the field of computer science, artificial intelligence has been applied to various areas of science and technology. Already we have heard these terms AI, artificial intelligence, robotics, machine learning, expert systems that are associated with fifth generation computers. But today's topic is the advanced part of AI, that is explainable artificial intelligence. AI is an emerging branch in computer science which interprets the means and methods of making computers to think like human beings. Expert systems, AI techniques, and fifth generation computers are claimed to hold enormous potential for the improvement, efficiency, and industrial productivity. AI systems have sophisticated decision support mechanism based on an enormous amount of data that are processed and synthesized efficiently into complex models. However, due to the internal encoding or their level of complexity of the AI algorithms, many of these models can be described as black boxes and not accessible to humans. In the last few years, AI has achieved a notable momentum that, if harnessed appropriately, may deliver the best of expectations over many application sectors across the field. For this to occur shortly in machine learning, the entire community stands in front of barrier of the explainability, an inherent problem of the latest techniques brought by soft symbolism that were not present in the last type of AI, expert system and rule-based models. Underlying this problem fall within the so-called XAI, explainable artificial intelligence field, which is widely acknowledged as a crucial feature for the practical deployment of AI models. XAI refers to methods and techniques in the application of AI technology to understand the result of the system by humans. Thus, XAI is any machine learning technology that can accurately explain a prediction at the individual level. DARPA, Defense Advanced Research Project Agency, DARPA, and LIME, Local Interpretable Model Agnostic Explanations, were the first two most notable efforts to create explainable AI. The application areas of XAI are in biomedical, healthcare, legal sector, finance, transportation, security domain, natural language processing domain, robotics, and various engineering fields like control engineering, simulation engineering, computer engineering, cybernetics, safety technology, knowledge technology, etc. Lastly, I say about XAI is a nutshell as a trust before intelligence. thanking you all for giving me the opportunity to deliver the theme of topic here today. Now this is the time to hear from our learned resource person, Professor Ravindra sir. Over to coordinator Alok sir. Thank you all.
Thank you, sir, for highlighting the topic to our participant. Now may I request Dr. Ravindra Kumar Jana from IMT Nagpur to share your thoughts and present on this applied and exploring topic, explainable artificial intelligence to the scholarly participant. This is the lovable time to hear from you, sir. Over to Ravindra, sir. Okay, sir.
Am I audible? Am I audible, sir?
Yes, sir, visible, sir.
Audible?
Yes, sir, visible.
Yes, sir, visible.
Right. So, very good noon, all of you. And first of all, I want to thank the organizer of this webinar, and especially the leadership of Dr. UC Pati, principal of Salipur College, and his team, taking so much effort to organize this type of events. And the theme is very good. That means you know that nowadays there are lot of advancement in different fields, and all the advancement in all these fields are anyway is related to mathematics. So mathematics is the mother of all the development across the globe. So that's why the application of mathematics is everywhere. And the theme of this webinar is also suits today's need, and that is the application of mathematics in science and technology. So I also thankful to Professor Alok for giving me the opportunities to be the part of this webinar. So we'll discuss about explainable artificial intelligence. We are all talking about artificial intelligence, machine learning, robotics. All has attained their heights in some sense. Even if we need some more applications, more advancement in that domain. So last few years, if you see, people are made advancement in machine learning, and the application of machine learning in your daily to daily life can be it as a product sector or a service sector. Nowadays, different companies, if you take example recently, Hero Honda has created a robots which can contact to the customers, take their specifications, suggest them suggest them according to their needs, and optimize the resources of the organizations. But the difficulty is that how can we trust that robot? How can you detect that the decision or the process undertaken by the robots is correct? That is the question nowadays. Even if you see in the last quarter of first quarter of 2020, European Union has passed a bill, that is right to explanation. Also the US Senate also trying to adopt such type of bills, because in these advanced countries, most of the tasks are being automated. That means you are getting result from the computers or robots or machine learning systems. But how do I believe that system? How do I challenge my things in the law of court? That is the big challenge nowadays. That's why people are more interested in finding how the artificial intelligence systems give the decisions. That's why this is called explainable artificial intelligence. How can a human being or the user explain why a decision is taken by a machine? Okay, so we'll start. So my PPT visible, all of you?
Yes, sir, visible.
Okay, thanks. You see that we'll start with the intelligence. We'll see what is intelligence. How do you make the system intelligent? That is artificial intelligence. Then we'll talk about the need of explanation of the decision taken by the artificial intelligence machines, and we'll see the recent development and research agenda regarding that explainable artificial intelligence. So we'll start with. So the first question, as a human being, what involves in my intelligence? How do I say that he is intelligent? He is not. How a human being show the intelligence? To make a machine or to make a human being intelligence, what are the things you need? The first thing is that you should have the way to perceive the nature. You should have different touch points to sense the environment. If you don't have that, then you cannot collect information from the outside world or your surroundings. If you don't collect information from the surroundings, you never be an intelligent person. So the first thing, you should have the way to sense the environment. So once you sense the environment, means in computer terms, we collected data from the surroundings. Once we collected the data, it is not enough. You should learn from the data. How do I learn from the data? Then I can apply the logic here. So I can apply the logic with my collected data, and out of this logic, I can find the reason why it is happening, why it is not happening. So this is the second step, means that is called learning. So learning from the data which I collected from the environment. As a human being, how can I collect it from environment? By seeing, by talking, by sensing, everything. These are the different sense organs the human being have, where he can use these organs to collect the information from the surroundings. Second, by this surrounding information, he can learn. And third one, to become intelligence, you should be able to apply this learned logic or learned intelligence to the practical situations or real life situation. So if you able to learn this intelligence you gain in a practical situation, then only people will be intelligent. Similarly, a computer system also does the same thing. First it collects the data, then trained itself to answer all these queries which can be expected based on the data, and apply his own intelligence in a real situation. That means ability to interact with the world. It can be speech, vision, motion, manipulation, whatever may be, based on your sense organs. For a human being, for a machine, based on different sensors. Ability to model the world and reason about it, find the logic about it, why it is happening based on the data. Finally, to learn from this logic and adapt it to the real life situations. So these are the three prominent components of any intelligent system or anything. Even if a human being, if you want, he is intelligent, she is intelligent, that means he has all these capabilities. So, but the main theme here is how to make the system intelligent, how to make the computer intelligence. So that is why an area that is called artificial intelligence has developed. What is the objective of that? The objective of artificial intelligence is the simulation of human intelligence by the machines. The process is same. Learning, that is acquisition of information, rules for using information, reasoning, find the logic, relate them, describe them, diagnose them, using different technologies, and then finally self corrections. That means you learn by itself. The system learns by itself. Gradually, once the system learns, then if the system learns all the aspect, all the dimension of a particular area, then you can say that system is an expert in that area. That means you can say this is the expert system for the area. Take example. Suppose you created an expert system to diagnose your disease. That means once you give your prescription to the system, all the element of a prescription, the system will diagnose and find out your disease. That means that system is being trained all aspect of medical sciences. Then only it say that it is the expert system or artificial intelligence system for that particular area or particular domain. So what is the goal of AI? Basically to build a system that exhibit intelligent behavior or to understand intelligence in order to model it or to find out how and why it is happening. Main advantages of artificial intelligence over human intelligence. How you can compare human being and the artificial intelligence. So few of these, there are many disadvantages of artificial intelligence if you compare to human intelligence. Human are more superior in adapting the situations, but system cannot adapt the situation very quickly. Adapt a system, system or computer or artificial intelligence or machine learning systems require many days, even if many years to adapt. But human being can adapt the situation very quickly. But where the human being, where the artificial intelligence oversees the human beings, these are the points. So systems are more quicker than the human being. If you give 3 inputs, if you say 3 plus 5, human can do very quickly. If they find out the square root of some 8-digit numbers, human will take times to do that, but computer will do it very quickly. So if the input are large, in that case, computers are more faster than the human being. Second, the human being can have some fatigue, boredom, tiredness, but that does not exist in the machine. Machine can work 24/7, but human cannot. That means the machine can give you the intelligent advice 24/7, 365 days in a year. Less biased. Human intelligence based on human nature itself is biased. So the decision, a human being takes the decision, there are a lot of elements of biasness. But this element of biasness is not there in the system. System work based on the informations. It does not have that biasness. So this is another advantages of machine over human. Or accuracy. The main concept of intelligence is the artificial intelligence is the accuracy. So it's have high accuracy in compared to human calculation, human brain. So these are the few factors where you can say that artificial intelligence has edge over human being. But the problem is, you see that the wave of AI, how it started. Once it started, that we say that it is symbolic AI, symbolic artificial intelligence. That time the technology are not that advanced, so we are using the very old language like predicate logic and other things. That means we are connecting the or finding the logic using the symbolic patterns. But what is the disadvantage of that system? The disadvantage is that that system has no capability of learning. They don't learn itself. They cannot do something extra. But in the human space, if a robot want to take the human space, the robot or machine learning agents must have the capability to learn from the environment and correct itself. That's why the researchers want some new ideas to be implemented in the artificial intelligence. That's why they develop another branch of artificial intelligence that is called statistical AI. In the statistical AI, the system may be learn from their experience and use their experience to solve the real life problems. That means the statistical model for specific domain train the data based on huge amount of data to make the system more intelligent or more applicable to a particular situation. But there is no conceptual capability and minimal explainability. That means suppose you take an example. So you apply for a loan, for the home loan, right? So once you apply for a home loan to a bank, suppose the bank has a intelligent system. The manager of that bank feed all your data to the system and finally got a decision no. But if you ask the manager why I got this message no, the manager is simply helpless because he don't know how the system derive the decision in that fashion. No, why system say no? The manager does not have any answer to you. Then if you have if you living in the European Union, so you have the rights to explanation. You can go to the court that all the parameters are good for me. Why should not a bank grant loan to me? In that case, as a company, as a bank, you should know why your system say no to that customer. That's why something more is required in this field. And that's lead to another type of AI that is called explainable AI. The system is capable of giving the decision, at the same time also capable of say why I take that decision, why not other decisions, other alternatives. So that's why this is happening, because all these things, all the advancement in artificial intelligence or any other technology per se, why it is happening like that? Why they are requiring that advancement every now and then? It is because first, data availability. We are now connected using social media, so tons of data are available to everyone nowadays. The problem is that we don't have the system to analyze it properly. So as the data is available and the infrastructure is also available, because we are now cloud systems. Suppose you say that you are experimenting some implementing some algorithms, that algorithm require high CPU power, and your computer or your laptop is not capable of doing that. So nowadays you can use the cloud, you can take help of thousands of systems from the cloud to execute your algorithms. And also you are now new different types of algorithms coming. Due to all these things, every area has modified itself and find out its application with respect to availability of data, availability of infrastructure, and availability of algorithms. And these are all the opportunities of all of these areas. Then you see that means most complicated things in the artificial intelligence nowadays, we say it is deep learning. Deep learning is the set of algorithms. It's a set of neural network algorithms. So how it is different from neural network? In neural network, generally, if you do some research, all these things, So there are three things. One is input layer, output layer, and in between there is a hidden layer. For basic research, any research, we took generally 1 or 2 hidden layers, not more than 2 hidden layers. So total 4 layers, input layers, hidden layer 1, hidden layer 2, and output layers, 4 layers. But using these 4 layers, there are some complex problem you cannot solve. So you need more layers in between. So once you need more layers in between, so you are giving more complexity to solving this problem. And once you are giving more complexity to solving a problem, the system itself becoming a black box. What is called black box? Black box means you give input, get output. You don't know how he derived the output. Also, you don't bother about how you get the output. So once the system is more and complex, systems of people are taking as a black box. Why should I go into the details of that? Why should I put my mind to find out all these things happening? So they treat as a black box. If you see some of the figure of the deep learning, you see lot of hidden layers are there. But you can say how that deep learning algorithms are work. Take here some example. Suppose you want your system to recognize some animals. So then what will do? You learn that you give the information of all these animals surrounding you to the system. The system will learn. System will learn itself how to detect, how to differentiate different animals. And once your system is trained, then you can show him a particular elements. Suppose you show him a dog. Whether the system is recognizing dog or not, that is the question. Then if you are building a deep learning system, different level has different tasks to perform. Suppose you give this picture dog. The first input layer will find out how the shape is, how big it is, how the shape, what is the dimension. All the dimension related things will be scrutinized at the first level. Second level, more smaller part will be diagnosed and detected. Third level, all the findings will be aggregated and matched with database from the learning phase. And finally he say it's a dog or a cat. So suppose your system say 90 times out of 100 it's a dog. So you say that your system performance is accuracy is 90%. Only 10% it's not detecting a dog as a dog. So this is the thing, this is the system. Our objective is to minimize this, minimize the error 10% to 5%, 3%, like these things. So the objective of this, but the problem is that suppose he say that it is a dog, it is not wolf. Then if you ask that user, if you ask the system manager there, why your system say it is a dog, why not elephant, why not other animals? But as a manager, as an administrator, as a owner, you don't have any answer to it, because your system is so complex, you cannot find why it is detect this, why not other. That's why you require some new system that can explain you the reason behind why it say it is a particular thing, not other thing, not other alternatives. So that black box, now what I discussed, create the confusion and doubt about the systems. So our objective nowadays, the explainable AI, the objective is to clear this doubt about the decision of a particular system. So suppose as a user you can say, why am I getting this decision? How can I get better decisions? You don't have any answer because it is a black box. At the same time, a customer, a business owner say, can I trust AI decisions? A customer can say, how do I answer this customer complaint? IT guys or operation guys say, how do I monitor and debug this model? A scientist say, data scientist say, is this model, is this the best model for this task or not? All are these AI system are decision maker will say that all these AI systems decisions are fair or not or biased. All these things cannot, if you don't answer all these things, then no one can rely on the machines. No one can believe on these machines. Suppose you take the first example. And in the deep learning, if you get this type of equation to get the results, there are more than 45 nodes inside the architecture, and each node has some responsibility. If you see, this is your formula. Using this formula, you derive the output. No one can infer how these numbers has come. If I change 0.44 to 0.35, what happens? So if you give this type of picture to the as an explanation, then no one can trust you. But if you use the explainable AI, then explainable AI, instead of giving this type of information for explanation, he will give like this. That means if you read this English-like statements, one can understand why a system say yes or why a system say no. So from the previously, the system used to give this type of equation. The AI systems are giving this fast equation fx. Nowadays, the explainable AI gives this type of explanation. And if you give this type of explanation, this is more human readable, more user friendly, more understandable. So objective is to every system should give this type of output instead of mathematical formulas. That is why the explanation AI aims to create suite of techniques that produce more explainable model while maintaining the high level of searching, learning, planning, reasoning, and performance. In performance, optimization, accuracy, precision, and enable human users to understand, and accept the trust and build the trust and effectively manage the emerging generation of AI systems. Take this system. Suppose that you give some data and your system they are sit in the black box. And within these black box techniques, your product which is there in your office or in your research lab or whatever will give some decision to the users. But if it is the black box AI, then these are the questions anyone can ask. Why did you do that? Why did you reject my loan? Why did you not do that? Why didn't you accept my loan? When do you succeed or fail? Why you say this is yes or this is no? Which part of the system is responsible for this result? If I am getting an error, what should I do to correct this error? This type of answer is not now in the artificial intelligence systems. To make these systems, to explain all these things, you require a different system that is called explainable AI. In the explainable AI, there is a extra component that is called explainable explanations. And that explanations, that means you don't say that the original system will be there. The original system will be there. The black box will be there. But here we add some another modules in the top of it, so that we can derive the nuisance or the fundamental how the system derive the decisions, and that will be there in that particular system. So the extra part of explanation IV is the explanation modules that will sit in the top of the black box. And once that black box give the result, the explanation, the interface will explain you regarding something. Then you can say that yes, I understand why it say no. Yes, I understand why it not said yes. I know that why you succeed or fail. I know that which part of the system, which part of the inputs decide the results. Or I understand the whole functioning of the systems. Once you understand the whole functioning of the system, you can trust it. Suppose your system is detects some of the birds in the environment. So your system, you put the system anywhere, then suppose some rooster comes and your system detects, yes, it is a rooster. Then you can ask question, why it is not called, why it is rooster, why not other birds? But if you adopt that explainable systems, then here that trick here. You see that before explainable systems, we have only this box. That box having this, if you say, we have this box, and here you see that if our system is explainable system, then I can find out these deep nodes. This node, I identify these deep nodes is responsible to decide the input to the output, and these are the important nodes which decide this is a rooster. And if I know these are the nodes, these are the logic which apply and say it is a rooster and is right, and then I can trust the system. That means I can verify the predictions, I can identify the flaw, I can learn from my mistakes, I can ensure the compliances to the legislations. That means you can use my system as you can use my system in the law of court and say that this is my system, and that's why I can get the output. And if the court agreed on the principle based on which you are getting the output, then so your system is good, your system is fine. So nowadays we have different techniques, we will see more techniques. One of the techniques is called sensitivity analysis, assay. So using assay techniques in black box system, I could find out what are the nodes or neurons are responsible to my output. And if I know these are the responsible to my output, I can easily track the results from the input to output. And that's why this is the advantages of explainable artificial intelligence. So similarly, we can take, so today what are you doing? Without the explanation, we are doing this. We are training data, we are learning process, we are learn functions. If once you give the input, the output say it is cat. But even if you are give the output as a input as a cat, and the system is saying it's cat. But the problem is, why it is cat, why it is not dog? Do I explain this to my customers or to my users? No. That's why user is worried. Why get this in output? Why not other output? If I am not getting the correct output, how can I handle the system? All these things are not happening now. And now, tomorrow, this is the responsibility of explainable AI system to do all these things. That means we have a interface which is in the top of your black box, which try to explain why a particular thing has been predicted by my system. So this is all about the explainable AI. Goal, you see that there are two things. So when you talk about a system, the first question comes in your mind that system, if it is not high performed, we cannot buy it. Suppose take example of COVID-19 vaccines. Someone saying is 90%, some is 90%, someone 70%. If you give an option, so you will choose that 91 because its accuracy is more than others. That means everything, everywhere we are talking about the performance. But the another thing is that with the performance, we should explain what is happening. That means the past year's AI rely on the predictions, accuracies, performance. Now the new AI, that is called explainable AI, now rely on two things, two parameters, not only the performance but also the explainability of the systems. That means you see that the performance in the today's systems or the generic artificial intelligence system, we are getting high performed things, high performed systems. But tomorrow we require a system, even if it is not that accurate, but it should explain the things better to me. So a better system is not the question of today's. It is the performance plus the explainability of a system. Ask anyone, do you prefer a system 99% accurate and no explainability, or a system 90% accuracy and 80% explainability? Definitely you can say that the second one I need, because I also want to know that how my system is work. So tomorrow system, even if we can sacrifice in performance, our objective to get both performance, the explainability. So there is a trade-off between explainability and performance. So we can have a system having both of the matrices. Okay, so this is the framework. As I told, this is the explanation, explainable AI framework, and in that we have added only one module, that is called explanation interface, and this interface is sit on the black box itself of our original systems. So measure of explanation effectiveness, then how to measure explainability? There are different matrices, different attributes where you can say in terms of explainability where your system stands. That is, first is user satisfaction. How much the user is satisfied with your output explanation. Clarity of the explanations and utility of the explanation. Then mental model. This is the new research topics are coming in the explanation, explainability AI. Now they find out, they want to model the human psychology into the machines. That means they can read the human psychologies, and based on that psychologies, the system can give you the answers so that the user can satisfied with the answers. So the mental model also another criteria to measure the explainability, how much the system read the mentality of the user. Understanding the individual decision, understanding overall model, strength, weakness of the assessment, what will do it, prediction, all these things. Then second one, the third one is task performance. How fast the decisions are coming, how fast the explanations are coming, whether the explanation improve users decision making capability. If it is enhancing the user decision making capability, that is good for me. So I can say that it is explainable for me. Artificial decision tasks, introducing diagnosis, user understanding, all these things. Trust. That means the appropriate failure use and trust. That means here the thing that how you trust it. Even if you know that your system predicting 90%, 10% may be failed. Then how you can remove that 10% ambiguities in your users? That is again the measurement of the explainability. and the correctability. That means how correctly you are identifying. If not identifying, why the 10%? How do I overcome this 10%? Then you should know that why this error is coming. And if you know why this error is coming in your system, you have enough way to correcting the error. So these are different parameters. You can say how much your system can explain the logic. Okay, so these are the different models generally used in artificial intelligence: neural networks, deep learning, support vector machines, graphics models. Different models are there, random forest decision tree, all these things. All are the models which have some predictability as well as explainability. So now the question is that, suppose you take decision tree. Decision tree is an algorithm which explain better you why he has taken the decision. But decision tree has least performance or least accuracy. That's why we should combine all these techniques to find a new techniques which can improve your decision making. That means this is the objective, to include all this to create this. Right? So this is the performance versus explainability. So we want a system which has, even if I compromise in the performance, we should have some explainability. So I'll take 5 more minutes and to conclude it. So the challenge problem in that explainability is that you have to find a suitable explainable models and also explainable interface. So if you don't find these things, so that cannot help you to win trust among your user in terms of explaining some output of the system. And these are, you see that this is the different advancement in the field of explainable AIs. These are the universities and different organizations they are working in different methods. Different methods in explainable models and different method of explainable interface. And here you can say, so different universities are taking all these tasks. And I'll just show you some case studies that happens in US. That means they develop, UC Berkeley has developed some explainable robots to drive the car. That means the humanless car. So machine will drive the car. And he used the explainable artificial intelligence into the system. That means you can say why, if you ask the question to the system, why you start, why didn't you stop? He can answer. Because the light has turned green and there is no other thing, no one is blocking my road. That's why I start accelerating. So all these questions, that means the system, the car itself answer everything. If you ask the question regarding any activities, any output is taken. So there are many case studies are there where they use the explainability of the artificial intelligence. So these are some news nowadays you can get regarding the explainable artificial intelligence. You can get many projects, DARPA projects, LIME projects, all these projects are there. Now you can see these are the different algorithm of framework recently being used in the field of explainable AI. Okay, so this is the starting point of explainable AI. So lot of scopes are there, lot of research ideas can be implemented, and lot of algorithms can be developed to complement the black box of artificial intelligence. And this is some references where I got the informations. And thank you. If you have any questions, you can ask me. Thank you.
Thank you, sir.
Thank you very much.
Sir, thank you for a great presentation, and your speech brought new insights from the current research. Sir, you maintained remarkable poise in the face of a potentially hostile participant. So, sir, you can also elaborately explain the exclamatory explainable artificial intelligence with human intelligence. Your talk will enrich the knowledge of the participant in this webinar, sir. Now, so please accept our thanks for a great presentation, sir.
Thank you
Now
very
we
much.
have arrived at the questionnaire session. Is there any question from the participant? Please, hands up or any written in the chat box. Is there any question to either to R.K. Jena sir or Tarakanto sir? No, what question?
What does conversational AI really mean?
No, this is questions for R.K. Jena sir. What does conversational AI really mean?
Okay, so you see that this is the you see that why we require the conversational AI. AI system, as you know, it's a black box. But with the black box, we cannot create trust among our users. So there should be some way where the AI system should converge or to have a conversation with the users. That's why the concept of explainable intelligence are nowadays coming into in our research agenda.
Okay, thank you, sir. Are you getting the participant? Another question is there. What is deep leap?
Actually, I want some more clarification of the deep lift. What does it? What is that? I want more clarification of the deep lift. Is that a algorithms or a framework or a concept? I don't aware of this term. If you can explain me what is that? It is a concept or algorithm or what? It is a framework. I'm sorry.
Another question is there. Difference between explainable artificial intelligence and responsible artificial intelligence. So please explain.
Yes, it's a good question. The responsible AI and the what is other? 1 minute. And reason that reasonable AI is the part of explainable AI. So you can say in this sense that the explainable AI is the superset of reasonable AI, because for explanation you require the reasoning. You require to say that why it is happening, why it is not happening. So both are contemporary to each other. Both can, you can say this is another name to the explainable AI.
Okay, sir, thanks. So another question is there. What do you need XAI in medical ML applications?
Okay, you see that. Suppose if you have developed a explainable AI for your as a doctor. Suppose you create a robots as a doctor using that explainable AI, and if you give your prescription to the robot as a input, and robot say that you have this cancer, then you have certainly you can make a shock that why I should have a cancer. I don't have some symptom. I'm not realizing any symptom. But if you are adopted that explainable AI, the robot is safe. You see, even if you don't see anything, any physical change, anything in your body, but these are happening inside your body based on your reports. That's why it is very essential to implement the explainability in your robots, whether it's a medical, whether it's any applications.
Okay, thank you, sir. So from point of mine, so I have to clarify from you. So what is the next research work in XAI?
I didn't get you, sir.
After that?
One second, sir. I didn't get you. Sorry.
How? What is the research work going on after XAI? Explainable artificial intelligence.
We see that after the long persuasions or very hard work using different tools and techniques, we have only 10% of human brain is implemented using the latest AI intelligence techniques. So we have to do 90% more to capture the human brain using techniques. We have only small part of our brain being automated by using the systems. We have to make a system which can automate the human being in 360 degree.
Okay.
So this is only the beginning of anything we can say.
Okay, thank you, sir. So another question for Tarakanta sir. Are you present here, Tarakanta sir? Hello.
Yes, sir.
Another question from Chirag Vishwarupa. Farm alive, farm tree becomes an example of a fractal or not?
Sir, I could not get you. Very much noise is in your background.
Hello.
Yes.
Tarakanta sir, audible?
Okay, Radha.
Am I audible?
Right.
Yes.
Another question to you, sir. So, Barn Salai farm tree, is this an example of a fractal?
Yes, of course.
Okay, sir. Thank you. So
That is actually Barnsley's form.
in our chat box. Hello.
Yes, sir.
So now, thank you again to Tarakanta sir and Ravindra sir for answering those questions and
Hello,
for
Alok sir.
presentation, sir.
Hello, Alok sir. Namaskar. Am I audible?
Yes.
I am Kanan Kuswandana from Dharmashala Mahavidyalaya.
Yes.
I want to know what Dr. Tarakant sir says. The factors look like a farm tree, or they form a farm tree, Barnsley farm tree.
Yes, what is the question, ma'am?
The question actually, sir, the factors look like a Barnsley farm tree, or they form a Barnsley farm tree.
No. Barnsley form is the name of that picture because Barnsley is the person who championed this study of iterated function system and fractals. So that is the name given to that picture. That's it.
Okay, sir. Thank you, sir. Thank you.
Okay.
Okay. It was a great pleasure to have you all with us. Now, I request Professor Rajendra Kumar Swami to cast vote of thanks. Over to Rajendra sir.
Good afternoon, everybody. Esteemed Principal, Dr. Umesh Chandra Pati, Honorable Resource Person,
Dr. Tarakant Naik, Associate Professor IIT Bhubaneswar, and Dr. Rabindra Kumar Jena, Professor IMT Nagpur. Lovable Dr. Sangita Mishra, Head of the Department, Member of Organizing Committee, all learned participants, including academicians, researchers, students, electronic media and print media persons. It is my great privilege to have been asked to propose a vote of thanks on this occasion. I, Rajendra Kumar Swami, on behalf of Mathematics Department, here together, and on my own behalf, extend a very hearty vote of thanks to eminent, versatile, two resource persons for gracing this occasion. In spite of their important work and sharing their views with us and our students. Now, I would like to acknowledge our deep sense of appreciation to Dr. Tarakant Naik for his explanation regarding science and technology to focus on fractals, geometry, and the list of known physical fractal system and its rapid growing in day-to-day life. I think this enriches the knowledge of our participants. Next, I may like to express our sincere thanks to Dr. Rabindra Kumar Jena from IMT Nagpur for giving an excellent coverage to the speech regarding the explainable artificial intelligence, which is an emerging topic applied in every sphere. This imparts the idea on the artificial intelligence with machine learning technology, which will be beneficial for researchers, faculty members, and students. I also wish to express my gratitude to our revered principal cum patron for gracing today's programs and guiding us to hold such international webinar. Thank you, sir. I would like to thank our beloved HOD, Dr. Sangita Mishra, for her moral support, rigorous effort and guidance to organize such type of e-meeting. Thank you, madam. I would also like to express hearty vote of thanks to our members of our organizing committee, Alok sir and Prashant sir, for presenting the theme and making this webinar interesting and meaningful. Lastly, I would like to acknowledge our gratitude to those participants who are gathered here on e-platform by our request and making this webinar a grand success. Finally, I would like to take this opportunity to place on record our hearty thanks to staff and volunteers for their perfect logistic support and guidance to make this webinar a huge success. Once again, I thank all of your cordial cooperation for today and also hoping for tomorrow at 10:45 am. Thank you, everybody. Mande Utkal Jala.
Thank you, sir. Great. Thank you all for participating in today's webinar. We hope to see you all tomorrow again with other two resource persons sharp at 11 am. Tomorrow after end of the webinar, the feedback link will be provided. Thank you all. Namaskar.
Thank you, sir. Thank you.
Now the session ends.
Okay.